Today, I'd like for us all to do some math. Anyone still there? Really? Great. See, math is kind of important, especially when it comes to calculating things like data density and swath width that can really help us plan and execute hydro surveys. But I know this stuff might be exhausting or even a little bit scary to some of you. So I'm going to leave a little picture of my dog up in the corner to provide some additional encouragement. So the first thing we should establish is a good firm understanding of the metric prefixes. These are things like kilo in kilogram and milli as in milliliter. This diagram here explains those prefixes in detail. You can change your prefix by dividing or multiplying by a number. For instance, 1 kilogram equals 1,000 grams, which you get by multiplying by 1,000. But why do you multiply by 1,000? Well, what you want to do when you convert between things is keep track of the units. In this instance, we want to cancel out the kilograms, leaving only grams, right? So let's take our 1 kilogram and divide it by 1, just to set up the fraction we're about to use. Then let's multiply by 1,000 grams over 1 kilogram. Since those are really just the same thing, all we've done is multiply by 1. But we also gave ourselves a way to cancel out the kilogram unit, leaving only grams, which was what we wanted to end up with. Nice. But what about going from kilograms to pounds? Well, in that situation, we would just say that there are about 2.2 pounds in 1 kilogram, just like there are 1,000 grams in 1 kilogram. It just changes the fraction you multiply by. Go ahead and pause the video and give it a try. Is this what you got? Great. Okay, now let's kick it up a notch and look at data density. Density is primarily dependent on the sonar system you use, which generally governs the amount of pings per second and the beam density, as well as the speed of the vessel. On Reason 7125 systems, you set a max ping rate, and the system controls that rate according to the range setting. If you increase the range as you go across a deep section, the system will increase the ping rate up to the max setting you have selected. Anyway, we were talking about data density, right? How do we go from ping rate to density? Well, let's start by looking at our initial fraction, which is basically given to us. Then, let's look at a common situation. Say we have a 1 meter surface, where each node represents a 1 meter by 1 meter square. According to NOAA specifications, we need to have at least 5 soundings, or pings, per node. So we really need to get from ping rate to pings per node. First, let's incorporate our speed. If we were going 7 knots, that would be 7 nautical miles per hour. But we need meters per second. Knowing that there are 1,852 meters in 1 nautical mile and 3,600 seconds in an hour, go ahead and pause the video and convert to meters per second. Is this what you got? Great. Okay, so knowing that we are getting about 3.60 meters per second, and that we are pinging at 20 pings per second, we can say that for every 3.6 meters traveled, we get 20 pings, or approximately 5 pings per meter. So every meter we travel, we get 5 pings along track. That sounds pretty good based on our density requirements. But that's just looking at one beam of the sonar. As you might recall from the Sonar 101 videos, a multibeam generates multiple beams, whose width depends on the pulse and the size of the sonar array. If your system has 512 beams, each one of those would generate 5 soundings across your swath every meter we travel along track. So it seems we need to figure out how to calculate beam width and the size of the swath to get a real idea of density. First, getting your beam width is going to require some trigonometry. Let's take one beam and look at it in depth. At 200 kilohertz, the Reason 7125 is going to generate approximately a 1 degree beam. Let's say the depth is 30 meters. If you split that beam in half, you get 2 right-angled triangles. That's convenient, because the tangent of the half-degree angle is the opposite side divided by the adjacent side. The opposite side is half of the beam footprint, and it's also the unknown here. So let's solve for it. Let's pause here so that you can do the calculation. Did you get 0.26 meters? Great. So the actual footprint is going to be twice that, or 0.52 meters. And that's it. That's the size of the beam in the across-track direction. Of course, the sonar is going to generate up to 512 beams, depending on how you have it configured, to cover an approximately 140-degree swath. Remember how we used the tangent to calculate the footprint of the beam? Let's try to do that same calculation for the footprint of the sonar itself. This time, instead of 1 degree, you'd use 140 degrees. Go ahead and pause here and give it a shot. Did you get about 165 meters? Great. You might notice that 512 beams, each with a footprint of 0.52 meters, adds up to a lot more than 165 meters. The reason is that, again, depending on the way you have your sonar configured, you might have some overlap between those beams. This is a good thing when you're going over an interesting feature, as you might want to get as many soundings on it or around that feature as possible. If the same sonar was set up to output 512 equidistant beams, or beams that are spaced equally along the sea floor within a 165 meter footprint, you would find an overlap of about 0.198 meters per beam. A beam that is 0.52 meters wide would only uniquely insonify a 0.322 meter wide footprint. Pretty cool. Okay, so let's actually come up with an answer to our original question. Do we have enough data density for a 1 meter grid node? Well, one beam is going to generate about 5 soundings within a 1 meter grid. With a beam width of 0.52 meters and an expected overlap of about 0.202 meters, I think we would find about 3 beams within that grid. That gets us about 15 soundings, well above the 5 soundings per node rule. So now we can do some basic math to plan for our density and coverage requirements. I hope this has helped some of you get back into doing arithmetic. Feel free to let me know if you have any questions or comments. Thanks for watching, and good luck out there.